Even the reason one, the last 4 months, we deal with vibrations in offshore Petronas platform. Kalau pergi ke Pantai Putri itu nampak dari jauh ada kapal laut yang punya Petronas itu tempat kapal dia loadingkan air kalau tak silap. Isi air dan unload air gitu. Kat situ ada piping dia vibrate lah. Piping besar, very large piping. I think 24 inch. Vibrating very excessively, and then we went there and to see what solutions we can provide. So let's say we have a piping, and this piping is resting. Resting means it's only placed above the support. So this one is support. It's not clamped. It's not held by any bolt or screw. It's just placing under the support. And this one is also resting. So that pipe is maybe continue. The length is continued, left and right. Okay, so this pipe has a fluid running inside the pipe. Yeah, maybe turbulence. So that caused the pipe to vibrate, let's say, in horizontal directions. Vibrating in horizontal directions. Okay. So this section of the pipe only. Okay, so that section of the pipe only, vibrating in horizontal direction. So if we want to make analysis, only in this section, so we limit our analysis only on that sections of the pipe. Okay, so we can model the pipe. Let's say the whole body of the pipe is moving. So then we can model of the pipe. We can model the pipe in single degree of freedom system. Very simple model. Single degree of freedom system. So where we have the mesh. And we have the spring, and also we have damper. Okay. So what is the element of mesh here? Accessibility. So what is the element of mesh? Empat ni elemen of mesh apa dia? Apa elemen of mesh?
The tube, doctor.
Huh?
The pipe.
The pipe also, and then what?
Part of the support vibrating.
The support is also resting.
Oh,
the support is not moving. The support is not vibrating. What vibrate is totally the pipe. So the mesh is the pipe itself, and then what else? Remember, inside the pipe you have the mesh as well, right? What is inside the pipe?
Water.
Cause the pipe to vibrate is the water. So the mesh should be mesh of pipe plus mass of liquid, mass of liquid inside the pipe, or effective mass we can say, because the mass is always moving. The effective mass of the fluid. Okay, what is the stiffness? What is the stiffness?
The support.
Oh, the support is not vibrating.
The structure of, I think.
Is that? Almost. If you're talking about stiffness, we're talking about what? We're talking about
Spring.
flexibility. We're talking about flexibility. Yeah. You cannot find any spring here. This is the concept that I must stress. So stiffness is something about flexibility. And you cannot find any spring. You cannot find any spring in this pipe. So what is the flexibility of the pipe? Is how the pipe connected to the support. So that's determine the flexibility of the pipe. Yeah. So in this case, you can write it down. Flexibility of the pipe. How flexible the pipe is moving. So because the pipe here in these locations is not restrained, the pipe is not restrained, it's just free moving. It's just resting on the spot. Yeah. So this kind of condition of the edge, we can say. Yeah, condition of the edge that determine the flexibility of the pipe. So we assume the pipe to move as rigid body. So the whole thing of the pipe from here, from A to B, is moving as a rigid body. Means in phase. A move to the right, so B move to the right as well. B move to the left, A move to the left. So rigid body. If the way the vibrations of the pipe is bending, hopefully you can imagine it. So if you look at from the top, so let's say this one is, we're looking the pipe from the top. So if the pipe is bending means something like that. Yeah, the way fiber is bending. So this is also the stiffness of the pipe. Okay, so that one is also stiffness of the pipe. So the value will be different with the value of the stiffness when it's moved in rigid body. Okay, so the pipe bending means the excitation frequency inside forced by the fluid may be different frequency. So that's why the pipe is bending. But in practice, if the pipe is bending like this, the vibrations, it's much more dangerous than the pipe moving a rigid body. This one is much more dangerous if the amplitude is high, because the pipe is bent already, so the structure is deformed. So the pipe can prone to damage much higher compared to the rigid body. So this one is most likely, the bending will be most likely if the pipe is restrained in this condition. So the pipe is clamped. Instead of resting, the pipe is clamped. So the pipe is clamped here. If the pipe is clamped, so motion in rigid body is not possible anymore, right? Okay. Motion in rigid body is not possible anymore because it's totally restrained, fixed restraint on these conditions. So the only flexibility of the pipe is to move like bending. Consider the support is very rigid. If the support is not rigid, the support is flexible, then maybe the support will bend. So the stiffness will come from the support. Yeah, but usually the support is, if you can see I-beam, I think you have observed this one at some point, the I-beam. Okay, so the I-beam is created to have the stiffness very stiff in the direction. So usually they use the I-beam. So very stiff. Okay, so remember the stiffness is the flexibility of the structure. Okay, ada soalan? So where is the damping coming from? Where is the damping coming from?
The support, doctor.
In case this one is not clamped,
The pipe.
yeah, the pipe itself. The pipe itself has its internal damping. Okay, so one of the vibration control in pipe is they put the snubber. They put the snubber. Snubber is like a shock absorber. So if the pipe is moving horizontal, so then they will put something to, like a piston, like a piston to absorb the vibrations of the pipe in horizontal. So this one is, if they make additional damping, so this one is the damper. Okay, that will be the damper. Additional damper is the value is much more higher than the internal damping. Okay, so that's modeling mesh spring and damper model. Okay, so then we continue with amplitude, phase, amplitude, frequency, and phase. Frequency and phase. So as a vibration engineer, this one is the what you have to deal with. Because when you take measurement, when you go out to Petronas to take measurement of piping vibrations, then you will have this information. You will have this information, the amplitude, the frequency, and also the phase. Okay. So in the ULAN, it's only the very basic of the information, very basic of the theory about amplitude of vibrations. So if you have the machine, this is the equilibrium line. Equilibrium line. Equilibrium line. So the machine is vibrating vertical. Yeah. Vibrating in vertical, the amplitude is 5 millimeter, let's say. So when we say the amplitude is 5 millimeter, maximum amplitude means it goes up 5 millimeter, okay, and goes down 5 millimeter. So 5 millimeter around the equilibrium line. When we're talking about magnitude of vibration, magnitude of vibrations. Okay. So if the machine is rotating machine, so it has a fixed frequency. Let's say the machine is running at 200 RPM. 200 RPM is in hertz. What is the value of hertz in RPM? RPM is 200. RPM is rotation per minute. So if you want to convert it in hertz, 200 rotations per minute. 1 minute is how many seconds? 60 seconds. So let's put it 300. So 300 divided by 60 is 5, right? So 5 hertz. Okay, so if the machine is rotating at 300 RPM, and then this machine has some imbalance, so it will force the machine to vibrate in vertical, assuming in horizontal is very stiff. So then you will observe 5 hertz frequency. Okay, so if we put it in the graph, so the graph will be something like with the sinusoidal, right? So what is the magnitude here? What is the maximum? Maximum is 5 millimeter. The frequency is 5 hertz. So means if this one is in time, so here, how many seconds? If it is vibrating in 5 hertz, how many seconds in here? Anyone can answer? If the machine is vibrating at 5 hertz, here how many seconds? So one cycle, One cycle. How many seconds here?
One second, doctor.
Huh?
1 second.
Where 1 second is coming from? Where does 1 second coming from?
Sir.
Huh? Any other answer? One cycle should be the period, right? What is the period? You know the frequency, and you should know the period. What is the period?
0.2.
Yeah, 0.2, right? So T should be 1 over F. So 1 over 5, so 0.2 seconds. So that one will be 0.2, this one 0.5, 0.6, and so on. Okay. So if you take the sensor, if you put the sensor accelerometer here and then you measure, and then the analyzer or the recorder will capture the signal. Will capture the signal. So that one you will expect it to be 0.2 second, 0.4 second, and so on. Okay, with the magnitude of 5 millimeter. All right. So in equations, if this one is xt, so you can write down 5 sine omega t plus, this is the phase, millimeter. So omega t is 2 pi ff. Omega t is 2 pi f. So you have f equals to 5. Huh? So that one will be 10 pi. So this one is 5 sine 10 pi t plus the phase. We don't know absolute phase of the machine. Right. Okay. So this is the amplitude in millimeter, which is what we call it displacement. Displacement. But in practice, displacement is rarely used. People will not use displacement to say the amplitude of vibrations. It's not very frequent. The most common one is velocity. Most common one is velocity. So if you have the information of displacement, these equations, what is the velocity of the vibrations? Amirul, Izzuddin?
Yes, sir.
Amirul? Amirul
Yes, sir.
Amirul. Berapa Amirul? Displacement ada, velocity dia apa? You have the displacement as a function of time.
Yes.
So to calculate the velocity, what do you have to do?
You divide by time.
Divide. Not really divide. Apa dia?
Apa nama dia?
Differentiate.
Differentiate. Differentiate by time.
Okay, so let's say Vt is dxt over dt.
ET.
Yeah. So you have 10 pi in front of the time. So dia boleh pergi ke depan . So 5 multiplied by 10 pi. So cos jadi apa? If you differentiate sine, will be cos . So cos 10 pi t, yeah, something like that. So this one is millimeter over unit jadi apa?
over S.
Yeah, meter per second. Yeah, so you got 50 pi cos 10 pi t millimeter per second. Okay, so what is the magnitude of velocity now? Which is 50 pi, 50 pi millimeter per second. Okay, so if you want to know the acceleration, then this one should be dvt over dt. Yeah, so you get the 10 pi out of the equation. So you have 500 pi square sine, this should be minus 10 pi t millimeter per second square. So when people ask what is the magnitude of acceleration, your answer is 500 pi square Don't say minus because vibration doesn't have minus. Minus is just to say velocity and acceleration is different phase at 180 different phase. The minus. Okay. So in practice, the sensor we call it accelerometer. Accelerometer, which means it measures the acceleration. It measures the acceleration. So what you have is you have the acceleration in your data, and then with mathematics you can convert the acceleration into velocity, which is using integral, right? So you have acceleration, you want to go back to velocity, you have to integral. So the analyzer will do that. The analyzer inside your machine will do the integral, and then you got the information of the velocity. Okay, ada soalan? Ada?
Sir.
Ah.
I think the phase angle is missing already, right? For
Yeah,
the
the phase-
differential.
Yeah, you can put it whatever angle here. I think in mathematics you still have the angle, but that will be different angle compared to the previous one. Will be different angle. So
Oh,
what is
okay.
what is the application of angle? What is the application of phase? Anyone can answer? What is the importance of us to know the phase? So you got this data amplitude, that's fine. You got the frequency, that's fine, which is very important. And what is the role of the phase? What's so important for you to know the phase? In application, amplitude is very obvious. Amplitude is certain machine has, according to international standard, ASME is Association of Mechanical Engineers. So they put the standard. If you have the machine and then you put it on the floating floor or you put it on the rigid floor, and then they will put the value of amplitude. The machine cannot vibrate 12 millimeter per second. Yeah, cannot vibrate 12 millimeter per second. If the machine vibrates 12 millimeter per second, that means you have to do something to reduce the vibration. That is the international standard, the amplitude. But phase, what is the importance of phase? I think at some point you have done a little bit of the activity.
To determine in phase or out of phase, doctor.
That's true, but you said something which is in mathematical language. Okay, in practice, in language of engineers in practice, when you want to explain for the person whose background is not vibrations, what is the role of the phase? Because people who is not the background of vibrations, they don't know out of phase and in phase. They don't know that. But you have to communicate somewhere. At some point, what is the role of the phase?
So that the vibration moves in the same order.
No, if someone asks you, okay, you have the information of the phase here. What is this? Can you explain to me? So what you should explain? In this data, you have the information of the phase. So what is the functions of knowing this data, the phase? How do you explain that?
to describe the motion of the system.
To describe the motion of the behavior of the vibration, right? Okay, so let's say this machine here. Okay, this machine here it can move vertical. Okay, if you take this one point A and point B, because in vibrations, if you go in practice, if you go to the platform, oil and gas platform, you cannot say by eye. Yeah, with this type of machine, you cannot say by eye. For the type of piping vibrating, the very big piping vibrating at low frequency, you can see that by eye how the pipe is moving. But that one is the case of very big structure and move in low frequency. But for this kind of machines, the motions is a bit high frequency. It's not 2 hertz, it's not 1 hertz, maybe it's more than 20 hertz. So you cannot see by eye how the machine is moving. So when you say vertical, it's fine. But if you measure, if you got the phase at A, you got the phase 30 degree. You got the phase 30 degree. In B, at side B, you got the phase also 30 degree. So how is the motions of the machine? How is the motion of the machine?
In phase.
Yeah, in phase means A and B will move together.
Yes.
So it will move this kind of motions. A moving up, B moving up. Now, in different situations, when you find B is 210, the phase 210, and this one is 30. How is the motions of the machine? Alina ada?
The movement will be in opposite direction, Doctor.
Opposite direction mean what?
One will go up and one will go down.
Yeah, so the whole machine will what is the behavior? Can you describe the behavior of the machine? How the machine is vibrating?
When A goes up, B will go down.
Okay, so the whole body will rocking, right?
Yes, Doctor.
Yeah, so it will something like this one, rocking. Yeah. So we call it rocking motion. Yeah. So this one is a bit important of the phase. You have to know the behavior. So what is the important to know the behavior? Because we can know what is the problem. If the machine is rocking, so there is some function of the machine which is not properly working, so that cause the machine to rock. If the machine is rocking from side to side, maybe the connections of the feet, one of the foot of the machines, when it bolts into the foundations, is not so strong. So that's why it moves in rocking motions. So this is the kind of analysis that we have to carry on to troubleshoot the problem by using the phase. Okay. So one of the another applications is to determine the condition of the coupling. So let's say you here you have the motor. You have the motor to drive pump. So you have the motor, and then you have here the coupling. And this one will go to the pump. Okay, so here also we can determine the conditions of the coupling. So this one is coupling. Okay, so if we take the data here, and then we take the data here, and you have the phase which is 180-degree difference, means you have a bad coupling here. Yeah, means that this one is go up, this one is go down. So there will not a good coupling. Yeah, good coupling to determine means that there is a flexibility in the coupling. So you have to do something with the coupling so that everything is in phase. So that one is in practice as well, to troubleshoot the vibrations, the problem of the vibrations. So this one is not only vertical, but you have also to take it in horizontal. Because coupling, there are two, parallel coupling and also parallel coupling, and what is the other one? Angle coupling, if I'm not mistaken. I'm not sure. Forgot the name already. Okay, ada soalan lagi? Ada, kita review sikit Yang lain ada kat sini kan? Tadi cuma berapa orang aja yang cakap. Syahirah, ada Syahirah? Syahirah, Ajirah?
Ya, doktor.
Ada. Nurul Izzati ada?
Doktor.
Ada. Nak pastikan awak tak tidur. Nitesh Parameswaran.
Yes,
Are you
sir.
there?
Yes, sir.
Okay. Good. Siti Zulaikha.
Ada, doktor.
Okay. Right. Okay, jap Okay, kita play Kahoot to evaluate your understanding. Nampak Okay. So semua orang dah masuk. Kita play fun je. So pergi pada www.kabut.it. Okay, dah. Should be 60 eh. Okay, kita start eh. Masih ada juga yang salah. Ada 10 orang jawab mes nih. Oke. Masih ada yang jawab salah ya. Damping ni asal-asal jawab tu macam mana? Okay, next. Next time tulis nama aja, nama depan ya. Nama depan satu tulis, so jangan pakai number ni. Next. Dua 29 saya jawab Dim. Kenapa boleh jawab damping? The whole body. The whole body of a machine vibrate at 2 Hz. It's related to what property? The whole body, rigid body. It's related to mass. Okay, so this one is still lower ni, lower order thinking. Ni masih konsep aja, dia belum masuk lagi ke higher order thinking. Kalau nanti soalan exam nanti dah higher order thinking. So ni kena settlekan dulu nih yang konsep-konsep apa nama definition and so on ni, you have to settle it first. Next. Okay. Okay. Masih ada juga 9 orang salah. 3 meter per second. Ni kena detail tengok detail. Saya tuliskan 3 mm per second, bukan meter per second. Okay. Next. Siapa yang ada 171 ni siapa ni? P307 masih bertahan. Next. Tapi dari setengah ni masih salah. 8 tadi, ingat dia punya ni kan 8 second. So 1/8 0.125. Satu cycle tadi 8 second kan. Okay. Oh, 171 dah naik ke atas ni. 37 dah ke bawah. Next. Okay, masih ada juga. Salah, 9 dimping dia jawab. Phase tadi baru explain. Right? Next. Right. Masih ada juga yang salah. 10 orang jawab apa? 2 mm. Amplitude can be displacement. Makna millimeter can be velocity. Makna millimeter per second can be acceleration. 2 mm per second square. Kalau hertz ni maknanya dia frekuensi So yang bukan kan tanya yang bukan. Okay. Okay. Yeah. Stiffness, flexibility. Ya, element of stiffness. Sampai masih ada yang jawab mass of the ball. Should be flexibility. Next. 37 hampir mengejar. 4 poin lagi. Okay, good. So kalau elemen mass of the support boleh diabaikan, so dia just the camera. Kalau mass of the support cukup besar untuk contribute, mana dekat ujung tu kita kena tambah sikit effective mass dia. Okay. Okay, 171. Next. Ini sepatutnya 2 mm bukan 2 mm per second nih. So, saya salah nih. Sepatutnya ini 2 mm. Okay, good. Next. Okay, 5.1 radian. The phase absolute phase. So ingat the phase itu di belakang setelah T. Okay, so pi T kalau ada something 20T plus 2 makna 2 itu adalah phase. Jadi kalau saya balik kan boleh juga kan 2 plus 20T. So, makna 2 itu jadi tetap phase ya. Okay, yang melekat dengan T itu adalah frekuensi dia kan. Okay, apa juara dia? 0056 siapa? Satu tujuh satu siapa? Siapa nama? Hah?
Fikri.
Oke, Fikri ya? Awak nomor 1. Nomor 2?
Saya
Lu
saya
PW.
dulu.
Oh, awak tadi sempat juara 1 kan? Potong. Bagi asap sama Fikri. 56 siapa?
Saya
Dia pun over.
ya.
Oke, Tania. Alright, so ini kita untuk fun-fun aja ya. But at the same time is to know your understanding. Alright. So kita rehat kejap 5 minit. Lepas tu nanti sambung balik. 5 minit Okay, kita continue. Alright, so in the next sections, so akan masuk pada each element. The next section will discuss each element, stiffness element, mass element, and damping element. So this one is already with the mathematics. Okay, so stiffness element. So the idea is if you have everything is you have to determine what is the stiffness, or we call it stiffness constant. Stiffness equivalent element, stiffness equivalent constant, mass equivalent constant, and damping equivalent constant. So this is the basically the main idea in the next section. So you have mass element and damping element. Yeah, for each element, you have to determine what is the we call it equivalent stiffness constant element. What is equivalent mass and what is damping constant equivalent. So this is basically what you have to do in the next section. Okay, so stiffness element. We discussed first stiffness element. So basically, the stiffness element is determined by the constant which we call stiffness constant. So if you have, let's say, a spring, a very simple model of a spring element, stiffness element. Okay, so if you press the spring, and the spring will suppress by, let's say by X. So you give the force F, and the spring will suppress by X. So we can determine straight away the stiffness constant of the spring, which is F divided by X. So X is actually determine the flexibility, the flexibility value of the spring. Flexibility value of a stiffness element. Okay. Now, let me test the understanding. I will call your name randomly. Nur Ayuni. Ada awak? Nur Ayuni. Nur Ayuni tidur. Nurul Izzat. Ada. Nur Ayuni ada. Ada?
Toilet tadi.
Ada awak kan?
Apa?
Nur Ayuni ya? Awak Nur Ayuni. Okey. Okey, Nur Ayuni.
Ya saya.
So ini kita dah ada formula ni. Kita dah ada formula K sama dengan F over X kan? Sekarang ni kalau kita ganti dengan spring, sekarang ni ada spring satu. Sekarang ni kita ganti dengan spring yang K dia lagi besar. The value K dia lagi besar. Ya, kita ganti spring dengan K value lagi besar. F kita bagi sama. Force kita bagi sama. So X dia macam mana? Lagi kecil ke atau sama ke atau lagi besar?
Makin kecil kot.
Lagi kecil Kenapa?
Sebab F tadi tu besar, doktor cakap.
F tetap.
Oh, F tetap.
F tetap. K lagi besar. So X dia akan lagi kecil, sama atau lagi besar?
Rasa lagi kecil kot sebab K besar.
Sebab K besar
Sebab dia directly proportional
Yalah, kalau pakai feeding pun kalau K besar, maknanya dia lagi stiff Kalau kita tengok matematik, kalau ini besar, ini tetap constant Kalau ini besar, ini constant, maknanya untuk besarkan K dengan F constant, maknanya kita kena kecilkan X kan? Value of X kena lebih kecil supaya ini lebih besar kan? Alright? Good? Nur Aisyah? Nur Aisyah? Hidup? Atau dah makan tengah hari?
Dr. Wan
Nur,
Aisyah ke?
Nur Alisha. Nur Alisha. Ada Nur Alisha?
Yes, ada doktor.
Okey. Nur Alisha, kalau kita ada beam ada beam ada beam yang sama panjang lah. Beam tu dua sama panjang tapi K dia lain. K satu besar, satu kecil. Yang mana K yang mana kita lebih mudah kita bend. Kita bengkokkan. Alisha.
K yang kecil doktor.
K yang kecil lebih mudah kita bengkokkan. Kenapa? Kenapa Alisha?
Saya tak pasti doktor.
Mana awak jawab ini anak awak guess tadi kan? Kalau tak kecil besar So kebetulan awak yang kecil, betul lah jawapan tu. Pakai feeling lah apa? Atau pakai formula ni. Ada beam sama panjang, K satu besar, satu kecil. Bagi force yang sama, yang mana yang lagi mudah yang lebih bengkok yang mana? Yang lebih bend yang mana? Yang K kecil kan? Kenapa dia? Karena K lebih kecil itu dia lebih pakai keyword. K makin kecil K dia makin rigid ke makin fleksibel? Makin stiff atau makin fleksibel? Makin kecil K.
Makin fleksibel.
Makin fleksibel. So ingat tu aja lah. Okey, ingat tu aja. Kalau makin kecil K makna dia makin fleksibel. Kalau kita ada ada dua benda ni, satu daripada ada dua blok lah. Satu daripada besi, satu lagi daripada rubber. Mana yang K besar, mana yang K kecil. Kalau kita bagi force ke sini. K yang lebih kecil yang mana? Besi atau rubber? Siapa-siapa boleh jawab?
Rubber.
Okey, so rubber lebih kecil lah.
Rubber.
So ingat tu je Pasal nanti kita bawa konsep ni nanti dah masuk chapter 3 dan chapter 4 dan chapter 5. Kat situ nanti banyak soalan-soalan yang agak higher order thinking. So kena remember the concept. Okay. Alright. So basically untuk stiffness nanti awak akan cari equivalent stiffness. Equivalent stiffness tu makna contoh macam ni. Ni kita ada beam. Kita ada beam. Kalau kita bagi force dekat ujung, makna dia akan deflect. Ujung tu. Kalau panjang dia L, makna dekat ujung ni kita ada formula dia. So kita dapat K, stiffness constant dia adalah 3AI over L to the power of 3. Okay, formula dia. So E adalah Young modulus, I adalah second mass moment of area atau second mass moment of inertia. Okay, so berapa tebal beam berapa, dia punya width lebar dia berapa, yang I. Ada formula dia ada nanti semua kat table, tak payah hafal. Okey, kalau kita tambahkan spring dekat sini, spring K dekat situ. So berapa dia punya total stiffness? Total stiffness at that edge, at that dekat ujung ni. So dekat ujung ni berapa total stiffness dia? So nanti awak akan dapat konsep, kalau untuk konsep ni awak akan dapat konsep parallel dan inilah, parallel dan series. So untuk yang ini dia parallel karena dia sama. Kalau kita tekan beam ni by F and dia deflect by X, maknanya yang bawah ni akan deflect by X juga kan? Yang spring yang helical spring ni dia akan deflect by X juga. So total stiffness dia apa? Total stiffness dia adalah yang kita sebut dengan equivalent stiffness. Mana K untuk beam, ni kalau kita bagi nama KB lah, ujung KB, K untuk beam plus K yang helical spring. So ni untuk apa kita pakai ni? Kalau kita nak tambah mesh kat sini, let's say nak tambah machine yang rotating, dia ada mesh. Okay, so dia akan vibrate. So mesin ni akan vibrate. Mesin ni dia akan rigid body vibration. Tapi yang buat fleksibel ni adalah dia punya kedudukan dekat atas beam ni dan juga ditambah dengan spring ni kan. So dia akan vibrate. So yang jadi elemen stiffness adalah dua ni, beam dan helical spring. So kita perlu tahu dia punya constant. Okay. So kalau kita buat mesh spring and damper model dia, maknanya K ni adalah K, kat sini adalah K equivalent. Okay, so yang ini adalah mesh daripada mesin tu plus mungkin sebagian mesh daripada beam ni, M efektif daripada beam. Kalau deflection dari X adalah X, sebagai dia punya X. Okay. So stiffness equivalent. So nanti boleh pakai ini juga, potential energy. So setengah half K X square. Okay, so itu stiffness element. Mesh element. Mesh element konsep juga sama. So kalau kita dah main dengan sistem yang banyak dia punya komponen. So let's say K ini ada mesh punya X. So dekat sini pun ada bukan helical spring, torsional spring. Kat situ pun ada torsional spring. So yang mana elemen of mesh dekat sini? So ni pusing theta. Dia punya displacement theta, yang mass kat sini dia punya displacement tu x. So yang ni dia ada moment of inertia J dan mass dia juga M1, yang ini M2. So elemen mass tu yang mana? Ada berapa elemen mass? Nicholas. How many element of mass, Nicholas?
Can you repeat?
How many element of mass? In this system, how many element of mass?
One.
One. Which one?
The M2.
M2. What about M1? So we have two element of mass. Yeah? So the first one is the pulley itself. Pulley. And also this mass. So we have two element of mass. Okay. But the whole thing here is single degree of freedom system. Okay. Because theta and x is related. Kita pusing the wheel, so dia akan terangkat M1 ni. So dia akan related, dia bukan independent. So dia, the motions of M2 is not independent with the motions of M1. They are dependent. So single degree of freedom. So if we want to model the mass of the system, then you have to come up with equivalent mass. What is the equivalent mass? And also the stiffness. What is the equivalent stiffness? How many element of stiffness here? Ricky. Ricky, how many element of stiffness?
Satu.
Mana je?
Ya, spring.
Spring ni. Yang torsional spring ni tak masuk. The torsional spring. Masuk atau tak masuk?
Masuk.
So ni masuk juga ni K, ni dia punya, ini kita sebut KT lah. K dengan KT. So masuk. So ada dua element of spring. Ni K ni MKT. Okay. So then we have to come up with K equivalent. Yeah. So the whole system, what is the amplitude we want to represent, yeah, as the reference amplitude, as the reference coordinate. So we want to express that at xt. Boleh. So xt. So then what is the equivalent stiffness with respect to xt? What is the equivalent mass with respect to xt? Okay. Equivalent mass, we will use kinetic energy. Kinetic energy. So half. So how many element of mass in this case we have? So we have two element of mass, right? So first we have the pulley, which is rotating. The pulley is rotating. The center of gravity is at the middle, so but it's rotating. So then the mass should be rotational kinetic energy, which is a half multiplied by second mass moment of inertia multiplied by its velocity. But rotational velocity, what is rotational velocity? You have theta, so means you have theta dot. Yeah, theta dot means d theta over dt. Remember velocity? If you have x, if we have velocity, then it should be dx over dt. So we call it x dot, yeah, or velocity, or this one we call it omega. Okay, so a half j, we put it omega square. So plus, so this one is for pulley. What about for this mesh? So this mesh is not rotating, but it's only moving in x, linear. It's not rotation, but it's linear. So a half. Remember the formula for kinetic energy from your high school. So m2 plus x, sorry, plus its velocity, velocity square. Velocity means the velocity of m2. Let's say v2 and let's say omega 1. Okay, so this is kinetic energy. So then we say the reference is xt, right? So everything must be in xt. So a half j, what is omega? Omega is theta dot plus a half m2 v2 is x dot square. So what is the relation between theta and x? So you have if the pulley is rotating by theta, yeah, so that means this one will pull up by some value. So what is the here is x, and if you have the radius is r, then x is r theta. Okay, linearization. So you will come with the concept in the section linearization. X equals to r theta. Okay, so from here theta is x over r. So substitute here x over r. So a half j x, because you have dot x dot over r. So remember this one is square. Sorry. So this is square, plus a half m2 x. Okay, so everything is together. J over r square plus m2 x dot theta. Okay, so this is what we call M equivalent mesh. Formula is M equivalent mesh multiplied by x theta. Okay, so what is M equivalent? This is M equivalent, J over r square plus m2, which is r is the radius of the pulley. Okay, so you will come up with the same concept for the stiffness as well. So you will use the kinetic energy. So let's see for the stiffness, potential energy. So in potential energy, we concern only with the stiffness component. So U equals to 1 by 1. So how many components we have? So we have first component and the second component K. So let's go first for the second component. So the kinetic energy for this spring is a half. The stiffness constant is K. The displacement is x. So x squared. Okay, what else? Done with the first spring. So we go to the spring here, which is torsional spring. Torsional spring is moving rotationally. It's not linearly like this one. So kita pusing dia by theta, dia baru berubah dia punya ni. So for rotational spring, the kinetic energy is K, a half, K torsional stiffness constant, KT. What is its displacement? If linear spring displacement is X, so displacement for rotational spring is theta. So theta square. Again, our reference is X here, the displacement of the mass too. So everything must be changed to X. So what is theta in terms of X? We have it here already. Theta equals to X over R. So a half K X square plus a half KT X over R. X square over R square. So then you have a half K plus KT over R square plus R square. So now you have K equivalent. Okay. So it should be very straightforward. This one is just to increase your analytical skill. Although in practice you will not use this one, but it's good to have an analytical skill at some point. Okay. You will use this one for a very rigid structure like a machine moving up and down, but in practice maybe you will deal with a very flexible element like the panel of the car, the panel of the aeroplane. So you will use finite element, the software and everything. But the basic, you have to understand the basic. Okay, so this is what you have to do for the next section, the stiffness, mass, and damping constant. Okay, the soalan. Kalau tak ada, cukup Ada yang nak tanya? Ada? Ada? Okay, so kalau tak ada, kita cukupkan. So continue with the activity. Remember please be aware with the deadline and everything. Alright, Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Thank you, Doctor.